Hey class, welcome back to behavioral psychology or behavioral statistics. Sorry, it's a psychology course, but it's yeah, that would be a totally different course. Sorry. Welcome back to behavioral statistics. We are covering chapter 14 today in this video. And I mean, if you're taking this course with me at OCCC, this is the last chapter that we cover in the course. If you're watching this from somewhere else because this is posted on YouTube, your class might go over other chapters that we don't, like 13 and 15. I don't cover those. Maybe at some point will, just to kind of complete the saga, so to speak. But for now, this will be the last chapter we're covering at OCCC. So we're kind of really taking two chapters, or I mean, in other courses this is taught together, but it is kind of like combining two big topics, correlation and regression, together. Related topics, but different kind of procedures that would occur statistically. So this is the first chapter, I believe, that we have kind of 2 pages worth of learning outcomes because we're covering two topics. So first thing, being able to understand Pearson R as a measure of variables of relationships, computing Pearson's R, using and interpreting Pearson R, and understanding what the assumptions and limitations of it are, testing hypotheses about population correlation, or rho, with a sample R, and then understanding the concept of partial correlation, Spearman correlation, by point by serial correlation, and then the phi coefficient. These are different. These are other alternative forms of correlation that you can use instead of our Pearson's. Pearson's is the typical kind of standard form of correlation, but depending on the variables you're using, there are other forms you might want to use instead. And then finally, our last couple of objectives will pertain to regression lines. So explain and compute the linear regression equation to predict y values, and then evaluate the significance of your regression equation. So we are getting back into a bit of hypothesis testing for both correlation and for regression. The tools that you're going to need for this chapter: sum of squares in terms of the computational formula and definitional formula for correlation. Fair warning, I'm going to show you an equation that I think presents the information in a simpler way, an easier way for me to understand, but whatever works for you. If you want to use the formulas that are provided by the textbook, please do. But when I was taught correlation, both as an undergraduate and a graduate student, I kind of appreciated the formula that I'm going to share with you. They both lead to the same place. My head kind of wraps around the equation I'm going to show you a little bit better. I'm not the most mathematically inclined person, and I feel like the equation I'm going to show you is just a little less messy mathematically, a little less intimidating for me. So that's why I included it. There's also a hypothesis or z-scores, hypothesis testing, and analysis of variance, things we've talked about in previous chapters. So hopefully some of this material we're bringing a material from 4 previous chapters that should be familiar to you, and then kind of adding it on to some new stuff that we're talking about for chapter 14. So here's a quick comic. I think kind of getting into correlation. I used to think correlation implied causation, but then I took a stats class, and now I don't. And then the response would be, wow, it sounds like that class helped. Well, maybe. So yeah, that's kind of the thing we're going to start with, is that correlation explains relationships, or it talks about the existence of relationships, but does not prove some kind of cause and effect. So let's keep that in mind as we're moving forward. So correlation is intended to describe the relationship between two variables, and we characterize that relationship based on its direction, whether it's positive or it's negative. Typically, we're talking about a linear relationship, straight lines. Some of the other forms of correlation we might use can be used for things that are not necessarily linear, maybe curvilinear, for example. And we measure the strength of our correlation from -1 to 0 to +1. -1 implies a perfect negative correlation. As one variable goes up, the other goes down. A positive correlation, a +1, perfect +1, would be if one variable goes up, the other goes up at the same rate. And then a 0 just implies there's no relationship. And then we assume these characteristics are independent. So here's a visualization. Typically, when you're talking about correlation, it's plotted on a scatter plot with an X and Y axis, like you can see on the right here. And all we're doing is taking this data, person A through N, they have data for their family income in the thousands, and then they have their student's average grade. I'm assuming that's either, I guess, GPA or maybe just average for a semester. But we can see there is a plot, person A, you're going to find 31 and then 72. I guess that's about right there. So you're going to have one plot for two data points. And we can already kind of see, you can almost kind of visually draw a line and we can see the direction that that correlation is going in, meaning we can probably see some kind of linear trend between as income goes up, we would also expect grade point average or average grade to go up. And you can just kind of visually see that from here. It clearly means, now here's the thing though, we cannot say that income is causing grades to go up because there's probably other factors at play. Like, for example, I mean, if you have more money, maybe you have more money to send your kid to a better, maybe a better school in preparation for college, to get those grade points up. Maybe you have access to a tutor. There's all kinds of factors that could be. Maybe there's more books in the home. I mean, we don't know. We can say there is a relationship between these two variables, but we'd have to unpack it and do some kind of experimentation if we really are trying to say one causes the other. So here's some examples of positive and negative relationships. Here's a positive, and typically when a positive, you're going to see the line, our linear line or trend is going to go from bottom left-hand corner going to the right. It's going to be moving upwards from left to right. And so performance in class, time spent studying, the more time you spend studying, we would predict your performance in class would go up in terms of grades or assignments or whatever. Conversely, for a negative correlation, you're going to see it's going to be sloping to the right, starting at the upper left-hand corner and going down to the bottom right-hand corner. So in this case, performance in class and smartphone usage, we would predict as smartphone usage goes up, performance in class likely goes down. I mean, think about it. If you're on your smartphone all the time, and like if you're in class and you're not paying attention, maybe you're missing things, you're maybe not likely to do as well. So these are just relationships. They're not necessarily saying one causes the other, because again, there could be other factors at play. We don't necessarily know what direction the relationship is going in. But anyways, that we can at least see. Sorry, my dog just walked in. I had to check on see which one it was. Hey, come here. You can come over here. Here's some other examples of different relationships because we measure correlation in terms of its strength, that scale of -1 to +1. Example A here is a perfect negative correlation. Again, you can see it sloping to the right. I believe B is an example of a zero correlation or just a very, very low correlation. And you can see the tighter the data is, the higher your correlation value is, regardless if it's negative or positive. The looser the data is, the more spread there is, you're not gonna have as high of a correlation. So this one is probably zero. Because you could probably draw a line here and we don't see a trend. You could draw a line here. We really don't see a definitive trend. We can see trends here. I think this one is like a 0.7 or zero point 0.8, maybe even 0.9 to be honest. But it's a positive one. This is negative. It's not as tight. But then again, tightness versus looseness kind of in terms of how well does it stick to that linear trend or not. That's really a good indicator of the strength of the correlation. So really what we're talking about is measuring the degree that two variables are related to one another. A perfect linear relationship, -1 or +1. We typically don't see those in like when we're talking about like things related to humans because, well, humans we're imperfect. The way we collect data is imperfect. So, I mean, there's all kinds of factors. We're just, maybe in nature, we're more likely to see kind of those one-to-one correlations. And I bet somebody's watching this video right now and is like, yeah, right. I can give you some examples. And I actually have an example later on that turns out to be a perfect correlation. So I kind of put my foot in my mouth, so to speak. But what we're talking about for the equation, when we're trying to find that correlation coefficient, we're looking at creating a ratio, and that value is we call it R, lowercase r. And what we're trying to measure is in the numerator is the covariability of X and Y, like how much do they vary together? And the denominator is the variability of X and Y separately. We want to like tease that apart and see. So the higher that numerator value is, the higher our correlation value is going to be, meaning there's a lot, those two things are connected. They're changing together, they're varying together. And so here's just a kind of another way of breaking that down. The numerator is looking at covariance. So how much do X and Y vary together? If it's positive covariance, X and Y go up together. If it's negative, when X goes up, Y goes down, or vice versa. The bigger the magnitude in terms of that covariance, is we're talking about a stronger relationship and a higher score of R. The denominator is the product of standard deviations. We're looking at the individual variances within X and within Y. So we're trying to normalize that covariance, how much X and Y vary individually. Without this, you're looking at a kind of you have to break things down in kind of the original units like dollars, feet, whatever measurement you're using, and that kind of makes it a little more hard. So when we use standard deviations, for example, we're standardizing and everything is kind of on the same page. So this bottom one here in the red is the equation that I really prefer to use. The equation that's given in the textbook gets you to the same place and is saying the same thing, but visually I am just somebody who kind of understands this a little more conceptually. Now, this equation we're going to look at later, this top one, this is using like if you want, you can use z-scores as well to compute R, meaning there are several ways that you can compute R, but it all kind of starts from this bottom equation. So what we're trying to do is we're gonna sum up, we're gonna take our individual scores, subtract them from their mean for both our X and Y variable, and we're going to sum that up, our summation symbol here. So really we're talking about how much do those individual scores deviate from the mean for each variable, and then that's over the standard deviation for X and the standard deviation for Y, and these are the procedures that you would use to find each of those variables. We will walk through an example using this equation later on, actually in a few slides. So if it doesn't make sense conceptually right now, it will make sense hopefully after we walk through an example. But this is how your textbook conceptualizes it. The numerator is called the sum of product deviations. So really, and it's the same thing I just showed you. This conceptually is the same thing as this. They just use the M, mean of X, mean of Y. Same thing. I just visually kind of like to see the X's and Y's together. I don't know. That's just me visually. So this is the definitional formula. Another conceptualization. This is more of the computational formula. Sum of X times Y minus the sum of X times the sum of Y over N. That's another way of conceptualizing it. Again, to find that numerator. I kind of find this one to be a little less messy, but use whatever works for you. It all leads you to the same place. That's fine. Again, here's a scatter plot kind of showing you this is only 5 data points, but we can kind of even detect somewhat of a linear trend even from that. And then for finding our standard deviation, what we're talking about is sum of squares of X, sum of squares of Y, getting standard deviation. So again, kind of same conceptual thing happening here. I don't know. I prefer to work within this realm, but if you're more comfortable with like sum of squares, like that's fine too. Just again, whatever works for you. Okay, so other things when we're talking about the Pearson correlation, you can express it in terms of z-scores instead. Z-scores will identify the exact location of each individual score within a distribution. Remember, on that normal distribution, so we can do our sum of our z-scores times z-scores of X, z-scores of Y over n minus one. If we're talking about sample data, if we're talking about population data, pretty similar concept, except instead of n minus one, we use n, our total population number. So that's another kind of a way we can use our correlation equation to find R. Here's an example, a really simplistic example of only using 3 data points. We have a researcher, they record the number of hours studied and exam scores for 3 students, and they're wanting to find out what's the relationship between hours studying and your exam scores. We have A, B, and C. And here's their scores for both variables. Student A studied for 2 hours and got a 65. Student B studied for 4 hours and got a 75. Student C studied for 6 hours and got an 85. So what we would do, we want to find the means for both variables. So all we do for our mean of study time is add the 3 variables up, divide by 3. That gives us a mean of 4. Same thing for our scores on the exam. Add the 3 scores up, divide by 3, we get an average score of 75. So we have those same data points for the same 3 people over here. Now to find our numerator and denominator, we are going to subtract each individual value from the mean, from our mean, and then we are going to, so we can see that here, 2 minus 4, 4 minus 4, 4 minus 2, I guess in this case. Oh no, 6 minus, I'm sorry, 6 minus, I was looking at the wrong column, sorry. Got distracted. And then we do the same thing for our Y column. We multiply those variables. We subtract, do the same thing with squared. Now we're talking about our numerator or denominator, excuse me. And then we have this stuff. We can actually go plug it into our equation. So on the next slide, we can plug in these values here for our equation. So really what we're talking about is 40 over the square root of 8 times 200, 40 over the square root of 1600. 40 over 40 gives us a perfect 1.0. This is the example I was talking about. This is a perfect correlation. Again, only talking about three data points. So if we had more, probably wouldn't, it probably would still trend in that same direction, but maybe it would not be quite so perfect. With three, it's probably more likely to see some kind of trend, perfect trend that way. So what we do is we would say this is a perfect positive correlation, and as study hours increase, exam scores increase as well in a perfect linear way in this three-person sample. So let's do a learning check real quick. A scatter plot shows a set of data points that fit very loosely around a line that slopes down to the right. So it's sloping down to the right. It's going from left down to right. Which of the following values would be closest to the correlation of these data? Is it A, 0.75, C, 0.35, C, negative 0.75, or D, negative 0.35? So pause the video. You might even want to draw it out. You might want to visualize it and think about a line that's going from left sloping down to the right with a looser pattern of data. Pause the video, think of your answer, then come back. Okay, hopefully you got your answer down. In this case, it's D. We know it's a negative correlation right away. We can eliminate A and B because if it's sloping to the right, we're talking about a negative correlation. And the key word, loose. If it's tightly to the data, the line, then we would probably go with C, but it's loose. We're going to see more spread of those data points. Okay, next one. True or false? A set of n equals 10 pairs of x and y slopes has a sum of x and some, I just don't love the way this one is worded. Equals sum of y equals sum of x times y equals 20. For this set of scores, our sum of products is 20 or minus 20, excuse me. And then true or false, if the y variable decreases when the x variable decreases, their correlation is negative. So pause the video, think about the equation we looked at earlier. I think the conceptual equation, you can plug some of those values in, and then you just want to make sure did the results come out to negative 20 or not. That's how you determine if it's true or false. And then think about what the question is asking for for the second true false. Pause the video for a moment, come back when you think you have the answer. Okay, hopefully you have the answers or you have your answers written down or somewhere you can check. First one is true. We can just plug those values in. 20 minus 20 times 20 over 10 gives us 20 minus 40 equals negative 20. And then the second one is false. If they change in the same direction, whether it's going down or going up in the same direction, that is a positive correlation. I know that might sound a little weird, but that's kind of what's happening. Correlation, they have different applications. They allow us to predict, kind of see what we think, what kind of prediction we think. We know there's a relationship between certain variables that allows us to maybe predict. Okay, if score on X is this, maybe that helps us kind of understand what we might expect the score on Y to be. Now that's starting to get more into like linear regression, but again, you can kind of see where the seeds are being planted. Allows us to quantify things like validity and reliability, theory verification. We can really verify a relationship between two variables, especially if that's kind of what our theory is based on. It would be nice to have statistical support or evidence that supports that. How do we interpret the information from correlation? It describes the existence of a relationship, but does not demonstrate causation. In order to demonstrate causation, we would have to use an experimental design that allows us to manipulate the variables that we're trying to manipulate some variables, control for other variables, and really be able to determine does X cause Y. Right now, we can only say X is related to Y or they have a relationship. So there's an example on 14.4 that demonstrates the fallacy of attributing causation after observing a correlation. And it's this one here, looking at the number of serious crimes paired with number of churches. There does appear to be a positive correlation there. But if you're assuming causation from this relationship, you might think, oh my gosh, are the serious crimes causing the more people to build churches in response to to create a more moral society, or the number of churches causing more people to be I mean, like it takes you in some really weird directions if you infer causation from correlation. So that's kind of just a nice example of maybe how to avoid that kind of that thinking. Also, there might be sometimes, depending on your data, the range of data that you're looking at might affect the correlation value. So in some cases, you might want to restrict the range of data. So like, for example, if you're looking at like grade point average and like student performance are based on like grade point average based on like what year you are in college, like are you a freshman, sophomore, junior, or senior. Maybe you have a theoretical reason for wanting to restrict that range and see what the relationship looks like for maybe a certain group. Maybe you only want to look at upperclassmen, for example. So this is what I mean is like maybe this whole data set is all of the data for all of the students that you're in your sample, freshmen, sophomore, juniors, and seniors. But maybe this range here is kind of where you're seeing the cutoff for juniors, and you want to really explore this. Now, if we look at the whole trend, we see a linear trend here. But maybe if we isolate our data and we start to look at one specific group or whatever, we see a different trend. If we're only looking at this, we don't quite see a linear trend here the same way we would here. So restricting the range can alter, the value of our correlation or value of R. Another thing that affects our value for R is outliers. These are data, whether X and Y values or both, that differ from our sample data, meaning they really stick out kind of like a sore thumb, so to speak. And typically these are defined by being much larger or smaller scores than the rest of the sample, and they really clearly stick out in a scatter plot. And what happens is they kind of one way or the other can impact that correlation coefficient of R. So, for example, if we have a data set of only 5 people, we have their plots scattered on X and Y variables. We don't really see much of a trend here. In fact, we can see that mathematically, the trend is there's almost no correlation there. Negative 0.08 is basically saying no correlation. And then, however, if we throw in this one outlier of F, we have a data set of 6 now instead of 5. That one data point pulls the data towards a linear trend, in fact, a really strong one. So, and you might have reasons for wanting to keep that data point in or throwing it out. Like you typically want to explain why or why you keep it or why you don't keep it. And there are reasons for why you do or don't. But just showing you kind of visually what happens, just one extra data point goes from having no correlation to a very strong one. So correlation and its strength, again, we measure it on a scale of 0 to 1, but it's important to remember that this is, -1 to 0 to +1, either way. But don't interpret this decimal point as a percentage or a proportion. Correlation is not a proportion. You can square the correlation. R squared will give you a proportion of shared variability, which we'll look at later on. And this is called the coefficient of determination. But correlation by itself is not a percentage or a proportion. So again, if you want to know how much the proportion of variability is happening, what you do is you square that value of R. So as an example, if we have a correlation of R equals positive 0.8, that means 64% of the variability in our Y scores can be predicted by the relationship with X. So R squared. So the higher that value is, the higher our correlate, or the higher the value is, the more covariability excuse me, shared variability between the X and the Y variables. So here's some examples of linear relationship, 3 different data sets, and you can clearly see the data, how some are clearly related and some are not. So like IQ scores and shoe size, really no relationship there. IQ scores and college GPA, yeah, there's some kind of relationship there. Not perfect, obviously, but having a higher IQ is a pretty good predictor of doing well in college. Not the end all be all, but it's a good place to start from, sure. And then annual salary perfectly correlates with your monthly salary. Over 12 months, that's going to give you that kind of perfect linear trend. So with hypothesis testing with Pearson correlation, it's computed from our sample data. And what we're trying to do is establish the correlation we're trying to look at, does this reflect back on the population? So we're trying to look at the value of rho, which looks like P, but it's the Greek letter for rho. Our non-directional hypothesis is saying that for a null hypothesis is going to say that rho is 0, that our correlation value is going to be 0. There's no relationship. But our alternative hypothesis is saying it's not 0. It's going to be negative or positive. It's going to be some kind of relationship there. If we want to specify the direction we think, will it be a positive or negative relationship? Then we have to write out our alternative hypothesis in a different way. So if we're saying it's a positive relationship, The null hypothesis is saying that rho will either be equal to or less than zero. The alternative is saying p or rho, excuse me, will be greater than zero. And then for directional for a negative correlation, our null hypothesis says p will be great or equal to or greater than zero, and the null p will be less than zero, which would give us a negative value. So here's a scatter plot looking at population and Y values with a near zero correlation, I think, but then you pick out these three data points and it might tell us something a little bit different. I think that comes out of your textbook. Read about that there. Here's the hypothesis test, and I'll actually walk through an example with this too. If you have a sample correlation, if R is used to test the population of rho, we're looking at degrees of freedom for hypothesis testing is going to be n minus two. So when you're going to look up that critical value on your t table, it's always going to be degrees of freedom n minus two. So if you use a sample of five people, n minus two is five minus two. Your degrees of freedom is three. You're going to use that F table. But here's the equation. It's R minus rho, so our sample minus our population over 1 minus R squared over n minus 2 square rooted, of course. I'll walk through that equation and it'll make a little more sense, hopefully, with an example in just a moment. But what do you do in terms of reporting your values? If it's statistically significant, you report the value of the correlation, your sample size, the p-value or probability level, and then what kind of test did you use, one or two-tailed test. So in this case, you might have a positive correlation at 0.65 with a sample size of 30. Our p-value was less than 0.01, indicating it was significant, and we used a two-tailed test, a non-directional test. But here's an example of actually hypothesis testing. A psychologist wants to know whether there is a significant linear relationship between stress and hours of sleep among college students. They collect data with N, so from N students, so we have a sample of N, and compute a correlation of 0.62, negative 0.62. So there's a negative correlation. Our hypothesis, remember, if we're going with non-directional, really what we're saying is rho equals zero. There's no relationship here. Alternative is saying, yes, there is a population correlation. There's something going on between these two variables. How do we calculate it? We calculate it by going with R, our value of R, so negative 0.62 times n minus 2. That's our degrees of freedom in this case. So that would be 10 minus 2 gives us 8 over 1 minus R squared. So R again, negative 0.62. So all you have to do is plug these values in. You can kind of see the math here. Negative 0.62 times 10 minus 2 over 1 minus negative 0.62 squared that breaks down to negative 0.62 times square root of 8 over 1 minus 0.3844 gives us negative 0.62 times 2.828 over the square root of 0.6156 gives us negative 1.753 over 0.7846, gives us an approximate value of negative 2.234. So what you do now is you would consult the table, your t-test table for Pearson's correlation, and you would look up the value. We have a degrees of freedom of 8 because n minus 2. Our alpha level is 0.05, and we're using a two-tailed non-directional test. You would then go find our critical value is going to be plus or minus 2.306. So what do? We compare that to our t-value we got. We have a score of negative 2.234 is less than 2.306, so we failed to reject the null hypothesis. However, if we were using a higher alpha level, that would have been significant. But most of the time, you're using 0.05 or 0.05. So just something to think about. Okay, so yeah, how do we interpret this? This is a negative correlation between stress and sleep, but it is not statistically significant, and you would report the values here. Okay, so Pearson's correlation has been developed for linear trends, linear relationships. Sometimes we have data, though, that is not linear. We have non-linear relationships, and we want to look at correlation values there. We also might look at ordinal scales for data. So some of these other alternative forms, we have Spearman's. phi coefficient, and the point biserial correlation. And we'll kind of walk through each of these a little bit individually. Spearman is using for data from ordinal ranks. So ranking, how people are ranked in terms of maybe their class. You're used to measure the relationship between X and Y when both variables are measured in ordinal scale, and then also maybe used at the measurement scale as interval or ratio when the relationship is consistently directional but not linear. So an example might be level of performance versus the amount of practice. So we do see a positive trend, but at a certain point, it starts to become curvilinear. The amount of practice just at some point just doesn't continue to add the same value to our level of performance. Here's another example. You might look at the relationship. We have values on Y and X, and at first we see a pretty stark linear trend, but eventually, maybe it becomes more curvilinear versus this is pretty just straight linear. If we have ties in terms of the rank, you can have tie scores. You could use a Spearman correlation for assigning the rank. You list the scores in order from smallest to largest, assign a rank to each position in the ordered list, and then when two or more scores are tied, you compute the mean of their rank scores and assign a mean value as the final rank for each score to kind of break that tie if necessary. You also have the special formula for the Spearman correlation. The ranks for the scores are simply integers, so first, second, third, fourth, all the way, however many you have. You can simplify the calculation by using D as the difference between your X rank and the Y rank for each individual to compute their R, and that formula is listed below. We have the point biserial correlation for measuring effect size with R squared, measures the relationship between two variables. One of those variables only has two values. It is dichotomous. It is binomial, meaning like male, female, yes, no. It's one of those that it only has one or two options. And I understand. I just said male, female. I'm very much aware that there are different way people categorize like sex and gender and things like that. I just mean in terms of if that's what you were interested in and you were only collecting data that way, that's an example of a dichotomous variable. Pass fail is another one. College graduate versus not college graduate, those are other examples. One variable then has regular numerical scores, and the point biserial correlation is kind of a special version of Pearson's. The effect size we're using is a t-test in chapter 10, R squared. Point biserial has the same value as the R squared that was computed from our t-statistic. And that tells us that the significant mean difference between our two populations from the samples. And our R statistic measures the strength of the relationship between those two variables. So it can be used in the same situation as an independent measures t-test like we covered in chapter 10. So a dichotomous variable is first converted to a numerical value, so zeros or ones. So you could convert like college graduate versus non-college graduate zeros and ones, and you can use that to categorize. Then you're using the regular Pearson correlation formula with your converted data. R squared then is used to quantify the effect size and determine the size of the actual correlation. T is influenced by the size of the correlation and also your sample size. Our phi coefficient, the last one, both variables are dichotomous. So it could be looking at college graduate, yes or no, male, female, or college graduate, rural, urban, something like that. I'm just making stuff up off the top of my head. Both variables, again, are converted into values of 0 and 1. The regular Pearson correlation formula is used with those converted values. And then R squared measures the effect size. Okay, let's do a quick comprehension check. Participants were classified as morning people or evening people, then measured on a 50-point conscientious scale. Which correlation should be used to measure the relationship? Is it A, Pearson's, B, Spearman's, C, point serial or point biserial, excuse me, or D, the phi coefficient? Think about what this is asking. Think about what kind of data we're collecting here before you answer. Pause the video and come back when you're ready. Okay, hopefully you've got your answer prepared. In this case, it's C, point biserial. We have one dichotomous variable, morning people, evening people, and then we have a traditional kind of quantified point 50 scale measurement on conscientiousness. Okay, next one, true or false. The Spearman correlation is used with dichotomous variables or dichotomous data. Remember, dichotomous means like yes or no. We have two options, hence the prefix of di. True or false, in a non-directional significance test of a correlation, the null hypothesis states that the population correlation is 0. So let's look at that first one, or maybe pause the video, kind of unpack and write your answers down, or keep them in your head, whatever you got to do, and we'll pause whenever you're ready to come back, or unpause. Okay, first one is false. Spearman correlation is used with ordinal or rank data. And then the second one is true. Null hypothesis assumes no relationship. So in this case, rho equals zero, as indicating no relationship in the population. All right, now we're switching gears to linear regression, linear equations and regression. Pearson correlation measures a linear relationship between two variables. We look at figure 14.3 in just a moment. It really shows that there's some kind of line through the data, and it really makes our relationship easier to see. When we use that kind of line, it shows measures of central tendency as well, and it can also be used as a prediction when we put that regression line. So the purpose of using linear equations and regression is to develop a procedure that defines a straight line that is the best fit for our data. We're looking for the line of best fit is the terminology you'll hear. So you can see relationship between GPA and your SAT scores. We can see there's a linear trend of that data. This is our line of best fit that captures what's going on between these two variables and minimizes the amount of error. And that's the purpose of the linear regression, is to minimize error and capture that relationship with a straight line. So linear equations are a linear relationship between variables x and y, and that can be expressed in the equation y equals b times x plus a. If you remember back from early, maybe it might have been algebra, maybe one of your early math classes, even in high school, you probably remember the slope formula, y equals mx plus b. That's the same thing we're talking about here, just different letters. Y and x are our variables. A and B are the fixed constants. The value of B is called our slope. Does the line slope? Which way does it slope, negative or positive? And the slope determines how much the variable changes or Y changes when X is increased by 1 point. So here's kind of an example of that. Total cost, total number of months in terms of a gym membership. The more months you stay, the cost is going to go up. Pretty noticeable linear trend there with that one. And we can use this line, this regression line, to capture that even with these three data points, even at that initial sign up, 3 months later, 8 months later, we see the same linear relationship. So regression is a method we use for finding an equation that finds that line of best fit. What defines best fit? Well, really what we're talking about is a line that minimizes prediction errors. We want a line that gives us the best ability to make predictions based off that linear equation. So mathematically, what we're trying to do is define the distance between each data point and the line itself. And what we're looking at is y prime is the value, is the predicted value. So the little sign above y is saying this is the predicted value based on the linear trend. And we're comparing y prime to the actual y values. We're trying to compare that distance. Y minus y prime is the distance each data point is from the regression line, or this is the error of prediction. And error just means like, error does not mean something negative. It doesn't mean something bad has happened. It does not mean a mistake has happened. It just means there's a discrepancy between what we have predicted and what we're actually seeing. We're not expecting perfection from the regression equation. We're just looking for it to minimize error. So it produces a line that minimizes total squared error of production or prediction, excuse me. This is called the least squared error solution. That's what we're looking for, the least amount of squares error. So this is what I mean. Our linear equation is showing this trend of the data, but here are the individual data points. Now notice they're not all on this straight line. Most of them deviate. Some of them deviate by more than others. Like this data point here is pretty darn close to the actual regression line. So we're not going to see a lot of error there. But this one, this is the predicted value here, and this is that distance of y minus y prime. This is y prime. This is what actually we see in raw. And so, we're trying to minimize those discrepancies. That's what we mean by error with the linear equation. So regression line equation is y equals b times x plus a. The slope of our line can be calculated again for that equation earlier, sp over the sum of squares for x, or b equals r over our variance for y over the variance for x. The value of the constant of a is determined by our mean of y minus our slope times the mean of x. So that's how you can find those values as well. Here's a linear equation. We have n equals x. We have pairs of scores. We have an equation of y equals 2x minus 1. We can see we have our mean value for y is 7, mean value for x is 4, and we can use those values. We can plug that into here and figure out, a, and if we know a, we can, it's pretty easy to find out all the other things too. So standard error of our estimate. Our regression equation makes a prediction. That's the purpose of the regression equation. And we're determining the accuracy of the prediction depends on how well those data points actually correspond to our data. So, like, how well does the line fit our actual data? And what we're looking at is the precision of that estimate is called the standard error of estimate. So we're looking at the sum of squares residual over the degrees of freedom. Another way of conceptualizing that is we're adding up all of those distances of y minus y prime, squaring that over n minus 2, and that's our standard error. So that's what we're calling residuals is just those differences. Sum of squares is just the residual, the differences. So here's a scatter plot again, y prime equals x plus 4. It's our prediction line. Another example there. Here's one. Here's the actual deviation scores if it deviated. Some of these points, still the same equation. Or here's what, yeah, same equation, but our data points not quite as tight there. Relationship between standard error and correlation. As R goes from 0 to 1, our standard error decreases to 0. So as the correlation goes up, we see standard error going down because our data is going to be tighter. It's going to be tighter to that line of best fit. Our predicted variability in our y-scores is the sum of squares of our regression, r squared times the sum of squared of y. Unpredicted variability in our y-scores is 1 minus r squared times the sum of squares of y. And then the standard error of estimate based on r is our sum of squares residual over degrees of freedom, or another way of conceptualizing that is 1 minus r squared times sum of squared of y over n minus 2, all under the square root. Okay, so how do we analyze our regression, whether it's significant or not? A sample correlation is expected to be representative of the population. So when we're talking about sampling error, this is, there's going to be some inevitable error, but we want to know, do the results of our sample, does it generalize back to the population? So we're analyzing our regression using an F ratio like we did with our t-test, or excuse me, with our ANOVA. And our mean squared is just simply our sum of squares divided by its degrees of freedom. What we're saying with our regression line in terms of our prediction. The null hypothesis says the slope of the equation, or B in this case, is going to be equal to 0. They're not going to affect each other. So again, just a reminder, mean squares for regression is just sum of squares regression over degrees of freedom. Mean squares residual, sum of squares over degrees of freedom. And then to find F, it's going to be regression over residual. What actually happens over or predicted, excuse me, over what we actually see. So here's kind of a breakdown of that. If you're looking at the sum of squares for y, for example, it's going to be r squared times the sum of squares of y. Residual 1 minus r squared. So what's left over times the sum of squared. And for degrees of freedom overall for y, n minus 1. Regression, it'll equal 1. Residual, n minus 2. Okay, learning check. A linear regression has b equals 3 and a equals 4. What is the predicted y if y prime for x equals 7? Is it a 14, b 25, c 31, or d cannot be determined? Fun fact, it is not d. You can eliminate that one. We do have enough pieces there to predict. So maybe go back to this equation for, where did it go? Yeah, y equals bx plus a. Go back to that, plug that in if you have it, and plug those values in. Pause the video, come back when you think you have an answer. Okay, welcome back. Hopefully you have it paused. Correct answer in this case is going to be B, 25. It's 25. So B is 3 and A is 4. All we're doing is multiplying B times X. 3 times 7 is 21 plus A is 4, giving a value of 25. All right, next one, true or false. Decide if each of the following statements is true or false. First one, it is possible for the regression equation to place none of the actual data points on the regression line, true or false. And second, if R is 0.58, positive 0.58, the linear regression equation predicts about a third of the variance Y scores. Go ahead and pause the video. Think about both answers. Come back when you have an answer. Okay, hopefully you pause the video. Hopefully you're back. First one is true. The line estimates where points should be, but there are almost always prediction errors. It's very rarely. I mean, you might have some data points that fall exactly on the line, but it's pretty rare, where there's going to be error And that's okay. We're trying to minimize the amount of error. And then second, when r equals 0.58, all we have to do is square that for r squared, and that gives us 0.336, which is roughly a third. And this is the output you would see in from SPSS if you're running a correlation. You're always going to see the one here because it's correlating to itself, variable one to itself. But then we have the correlation over here, variable one to variable two, 0.875. So that's a pretty strong correlation. And then we can see the significance level, 0.5, 0.052. I mean, that's right on the cusp of saying it's significant. I mean, if we're saying our significant level is 0.05, I mean, that's right on that cusp. I think we could probably round down to 0.05 and be fine with that. But any little bit higher, we're right on that kind of edge of significant versus not significant. And this one below is just same thing, but we're looking at variable two. You're going to see the inverse over here. Here is the output for your linear regression. We have an R, 0.847. That's our correlation, R squared, 0.718. Here's the model of our regression, our sum of squares and residuals, degrees of freedom, mean squares, and then our F value. And this also tells us whether our F value or our regression equation is statistically significant. And then you have your regression coefficients for our different variables over here. And again, we can look at whether or not it's significant. So here's the scatter plot. I think this is from 14.1 or 14.2. Sorry, I'm going to skip past that. We are at the end of chapter 14. That is all we're covering for this course. Thank you so much for your patience. Please leave comments if you have questions, or if you're in my class, just shoot me an email. But that's really going to be it. Thank you again, and hope you enjoyed this course. Take care, everyone. Bye.